Thank you for the award. So this is one of the crazy ideas we had in recent years. So we're going to present physical layer cross-technology communication via emulation. This is a joint work with Sujuni and myself at the University of Minnesota. So as we know, WAN is everywhere. So we use Wi-Fi to provide high-speed internet access. We use Bluetooth to provide connection between the devices in short distance. And we also use ZigBee to support energy-efficient applications. All these technologies complementary to each other, and they increase rapidly. For example, Wi-Fi, the number of shipments by 2016 reaches 1.8 billion, Bluetooth reaches 4 billion, and ZigBee reached 130 million. So based on the Gartner prediction, so we have 20 billion IoT devices by year 2020, mostly connected by wireless. Not only the number increases, but they diversify to meet different application requirements. For example, for the latest development, we have NB-IoT, we have LoRa and Sigfox. Those are designed for low-power wide area IoT applications. All these applications and all the technologies coexist in one single environment, then they have to collaborate in order to build an integrated IoT application. For example, in the smart hospital, so you can use a Bluetooth device, directly control a ZigBee-enabled thermostat. And also you need to collect those information, send to the Wi-Fi and up to the cloud using LTE. So in order to achieve ubiquitous connectivity, the natural question is how to interconnect and bring them. Of course, the straightforward answer should be, let's do a multi-radio gateway. So it's a good solution in many scenarios, but in other scenarios, it introduces extra hardware, cost, and deployment cost and complexity. Also, the traffic getting out of the gateway is a huge overhead. We believe the gateway solution is not suitable for ad hoc mobile environment because you need a deployed gateway in advance. Therefore, we're looking at a new paradigm called cross-technology communication. So enabling technology allow heterogeneous devices to talk with each other directly. Let's assume we have CTC already. What we can achieve? First, we can achieve low cost. We can reduce the complexity of the network. For example, in Wi-Fi, we can use a Wi-Fi AP control directly all the ZigBee devices in one smart home without multi-hop, instead of using multi-hop ZigBee mesh network. Also, CTC can support direct communication between the heterogeneous devices without pre-deployed gateway. Traditionally, we know that we want to coordinate the devices and avoid cross-technology interference. Then the way we use is that use CSMA, concurrent radio to implicit coordinate. Now you can talk with each other. Then we can support explicit channel coordination by exchanging message between the devices. Then we can extend the local mechanism globally across the technology. Therefore, we can design global RTS, CTS, we can design global TDMA. So today, my focus will be WEBee, how to transmit explicit message from Wi-Fi to ZigBee. Okay, so here's the outline. Let me start with the state of art. I want to go through a brief history of CTC research. So in MobiCom 2009, eSense used packet length to modulate information, allow communication between two devices. Gsense used a gap between the packet, and Huawei used a combination of packet lengths. In InfoCom 2013, in MobiCom, we use a beacon interval to modulate the information. We call all these solutions packet-level CTC because it only uses rough information about the packet length, gap, offset to convey the information. So a packet can only express a single or a few bits, leading to very low data rate. In contrast, let's look at the physical-layer CTC. Essentially, we want to emulate receiver's RF waveform. So we can achieve essentially the receiver's maximum data rate by looking at the in phase and the quadratic phase of the ICO signal. Here we are. So we are 16,000 times faster than the original, the other solutions, which only achieve a few bits per second. The design. Design is straightforward, very simple. So starting with a Wi-Fi sender, we construct a Wi-Fi frame, we select the payload, which this payload will emulate ZigBee signals. And we send out the Wi-Fi frame, and the ZigBee receiver will overhear the Wi-Fi frame and naturally ignore the header and trailer of this Wi-Fi frame, and then demodulate the ZigBee compatible signal. Then we get ZigBee frame. Simple. However, it's very challenging because we have two technologies. They have dramatic different characteristics. For example, Wi-Fi using QAM and OFDM, and ZigBee uses OQPSK and DSS. They have different rate, distance, transmission, power, and sensitivity. Transmitting a frame from Wi-Fi to ZigBee equivalent to essentially two people from two different countries speaking different languages. They're trying to communicate. Okay, where's the magic, right, to make that happen? So the key innovation in this work is called signal emulation, which is instrument at the Wi-Fi sender side. In order to understand that, let's look at how Wi-Fi transmits a frame. So you get a Wi-Fi frame, and with a certain payload, then you go through a sequence of channel coding, for example, scrambler, convolutional encoding, interleaver. Then you go through, you get the coded bits. With the coded bits, you can modulate, use a quadratic amplitude modulation over multi-subcarrier. Then go through post-QAM processing and send out a Wi-Fi signal. This is how Wi-Fi works. Now, we want to try to do emulation, signal emulation. Emulation is achieved via a reverse pass. Suppose you know what kind of ZigBee message you want to transmit. Then you go through post-QAM emulation. Then you go through the QAM emulation and then get coded bits. Then once you get the coded bits, you do reverse pass, channel coding, reverse engineering, and you get a payload. Now, you know the payload, then you just transmit this payload, then you get the desired ZigBee signal. Okay? And of course, technical details are very complicated. I don't want to jump into too much. Only thing I want to emphasize is the QAM emulation, which is the core of the design. QAM emulation, essentially you want to imagine you want to create a certain wave in the air. And if you look at the frequency domain, Wi-Fi should generate QAM and OFDM signals like this. Okay? Then this signal should mimic from the time domain perspective, it should be OQPS signal. Okay? So that's the whole process of QAM emulation. Of course, the key is that how we minimize the error in the emulation. Based on the Parcel theorem, essentially say, okay, you minimize the emulation distortion in the time domain equivalent to minimize the deviation in the frequency domain. Okay, so given desired time domain ZigBee signal, you just simply do a FFT, you get a corresponding frequency domain component. Unfortunately, you don't really have an infinite number of frequency domain components in the Wi-Fi QAM. You only can select a subset of QAM points trying to emulate. So the QAM emulation process is an optimization process to find the correct Wi-Fi points. Okay, so this is not that simple because there are many other constraints. Our goal is that to achieve this without modification of any sender or receiver. So there are 4 other challenges we address in the paper. First, how we do reverse channel coding. Second, how we deal with the pilot loss avoidance. Third, how we support the Payload CTC, as well as how to provide the link level reliability. I don't have time, so if you are interested, please look at the paper. Okay, so I want to summarize the innovative features of WEBee. We believe this is the first protocol that's a dual standard compliance. In other words, it's a part of Wi-Fi frame is a ZigBee frame. So our design requires no change in sender and hardware firmware. We send a normal Wi-Fi packet. We only change the payload, the IP payload. But we make no change in the receiver side, and we receive a normal ZigBee frame. Okay, in fact, a ZigBee receiver has no idea whether it's a sent from WEBee or it's sent from a normal ZigBee device. It's fully transparent. One interesting phenomenon we found is that we combine the advantage of 2 technologies. One, we use Wi-Fi, which, as we know, is a kind of high-power devices, transmit at 26 dBm. We terminate as big mouse. And when receiver, ZigBee is very sensitive because it uses DSSS, so it's very sensitive receiver. Now combine the big mouse and the good ear, we found that WEBee, in fact, has a longer range than Wi-Fi, although you send out a Wi-Fi frame. We also support the Payload CTC 1 Wi-Fi packet. Of course, that's clear. You have 20 MHz bandwidth, and ZigBee can only receive like 2 MHz, right? So then essentially, in our implementation, we support 2 transmissions, 2 different ZigBee devices. Remember, this is not a broadcast. It's called a simultaneous unicast. You can send different content to different nodes simultaneously. So our evaluation also shows that we support high mobility and duty cycle operations. Last but not least is that we achieve 16,000 fast CTC with 99.9 reliability. Okay, so let's get into the implementation evaluation. So we have 3 versions of implementation. First, we implement the laptop with authorized Wi-Fi chip. We also implement in the smartphone, LG Nexus 5. We also implement in the USRP. Remember, we don't really change any firmware and hardware. And receiver side, there's no need to change at all because you just receive, this part receive the Wi-Fi, the other receive the ZigBee frame. We did the experiment in the lab, hardware, outdoors, and each trial runs like 10,000 times with varying distance, transmission power, packet length, content, duty cycle, and mobility. So we have a lot of data there, but I can only point out a few key results. Let's look at the symbol error rate with data rate. And this is the result in MobiCom 2015, FreeBee. FreeBee can reach 99% reliability with 7.5 BPS free channel data rate. And us, so because we don't really, we look at the signal level, so we reach 63,000 BPS, which is 8,000 times faster. Theoretically, if there's a very little error noise, we can reach 250 kbps theoretically, which is the native transmission rate of ZigBee. This is the symbol level. Let's look at the frame level. A frame fails with 1 symbol error. Okay, the experiment we did is that we use a laptop or USRP sent to the ZigBee devices. It turns out we can reach like 50% constantly in many settings. Of course, you then say, okay, 50% is not good enough. Then we need an additional reliability mechanism, right? Then simple solution, you just say, oh, you just retransmit 6 times. Now the results indicate it's 99% reliability. The reason we do that, we just do it transparently. We don't. And if you want to add additional coding mechanism, such as repeated preamble and coding, you can have less number transmission, so you can boost up the throughput further. We also show that Payload CTC can be achieved by using the subcarrier index 5, 15, and 34 and 44. Then with 2 channels, we reach 16,000 times faster CTC. So next, I want to show the WEBee in action. What's wrong? Okay, so I think there's no sound. This is the ZigBee receiver. And then we have a Wi-Fi injector from sent to the receiver. And we showed this is the one-to-one communication from Wi-Fi to ZigBee. And also we demonstrate that we can do Payload transmission from one Wi-Fi to 2 ZigBee devices with different content. We're also trying to figure out how we can use this kind of technology in the commercial setting. So that's why we built an application called Smart Light Control. So we know that the GE has a solution to control the light bulb using a gateway. So it's about $53 after Amazon. So you can translate the Wi-Fi signal to the ZigBee using the link gateway. Also, it's a zero cost. Essentially, you just directly use Wi-Fi to control ZigBee device. Here's the demonstration. So this is LG Nexus 5. We can control the color intensity on/off the WEBee, on/off the ZigBee light bulb. So after we did that, then we just think anything we can contribute to the research community. So we spend time trying to build a service so that you guys can go ahead and download and use it. So we do have a WEBee payload generator version 1.0. So you please download and give us some feedback. We can improve further. So we believe that with the WEBee technology, then you can build a lot of things on top of that, right? So you use WEBee, then you can build channel access control across technology. You can coordinate different technologies. You can do neighborhood discovery, and so on. Okay, next, the extension. Maybe you might ask questions that whether signal emulation is a generic technology. Our answer is yes. Is that because we all continue to work on that, and we have census work to be published a month later called WEBee. So we can transmit from Bluetooth to ZigBee. Here's the demonstration. So we have a smartphone and control the ZigBee light bulb, and using Bluetooth broadcast channel, because Bluetooth essentially do fixing hopping. So we fix the broadcast channel. So we also have a latest work, which is kind of interesting that we can even use LTE, band 7, which overlap with ZigBee ISM band. It's really a challenging task because we need to penetrate 7 layers of channel coding and also 6-step modulation in order to make it. So here's the demonstration. So we have a smartphone there, ZigBee receiver, smartphone connect to the LTE station, and look at the screen, we send out hello message. Okay, to conclude, WEBee essentially is the first physical-layer CTC design. We believe it's a paradigm shift with significantly higher data rate. And it requires no change of the hardware and the firmware on both sides because we only manipulate the payload. Our work also indicates that signal emulation is indeed a good technology to build so-called lightweight SDR, right? Instead of USRP and the warp costs you like $1,000, you can have like $5 Wi-Fi chip, and you do a software-defined radio. Last, I think it's the most important is that with this enabling technology, we can bring a surge of new opportunity to the community so that you can rethink how we did so many works on the local mechanism individually, then how to bring them together so that we can expand many local wireless mechanisms such as coordination discovery across the technologies. Okay, thank you. So the technical support is available at our website. So I'm happy to take questions.